In today's lecture, we are going to start a new chapter in solid state physics. And in this new chapter, we will learn about the physics of semiconductors. Actually, this first lecture on semiconductor is just intended to introduce you the concept of semiconductor. You know, semiconductor is a very important material and vividly used in the construction of so many solid state devices. The complete solid state electronics is based on this semiconductor. You use diode, you use transistor and different type of optoelectronic devices. And all those solid state devices are made up of semiconductor. So actually this semiconductor brought a revolution in the physics. So it is a very important concept, and we will learn about this important concept in a series of lectures that will provided in my playlist. Okay. But as I have told you, the aim of this first lecture is only to give a brief introduction regarding this semiconductor. Okay. So now let us start to know about an introductory fact regarding this semiconductor. I hope you all know, on the basis of electrical conductivity or electrical resistivity, materials are classified basically in three groups or three categories or three classes. And what are those classes? You know, those are conductors, semiconductors, and insulators. Okay. We have already learned about the conductors. When you say conductor, that means metals. And you have already learned in this course the physics of metals in my previous videos. Okay. And now we are intended to know about semiconductors. Okay. As the name implies, semi means half and conductor. So this material is sometimes behaves like a conductor and sometimes behaves like an insulator. Okay, and that's why it is called a semiconductor. So how we can define this type of material, which is called semiconductor? You can easily see if the electrical conductivity or the electrical resistivity of a material lies between the electrical conductivity and electrical resistivity of conductors and insulators, then those materials will be called semiconductor. What does it mean? It means a semiconductor has electrical conductivity smaller than conductor but greater than insulator. Okay. And similarly, when you talk about the electrical resistivity of conductor is smallest. So the electrical resistivity of a semiconductor is greater than that of that of conductor and smaller than that of insulator. So if you denote the resistivity by the symbol rho, and this subscript C denotes conductor, okay, then the resistivity of a conductor is less than the resistivity of an insulator, and it is less than resistivity of this is semiconductor. Okay, yes, and this is less than from insulator. Okay, so if a material has electrical resistivity or electrical conductivity lying between the electrical conductivity and electrical resistivity of conductor and insulator, then those materials will be called semiconductor. Okay. In fact, when you we will learn after some time that actually the electrical resistivity or conductivity of a semiconductor depends on temperature. Okay, At different temperature, the same material will have different resistivity and different conductivity. So if you talk about a semiconductor at absolute zero temperature, in fact it is seen that at absolute zero temperature, if you will take a pure and perfect crystal of semiconductor, then its resistivity will be just infinite, just close to the value of the resistivity of an insulator, and it will not conduct electricity. So at very low temperature, or you can say at absolute zero temperature, a semiconductor behaves just like an insulator. It does not conduct electricity. Okay, its conductivity is zero and resistivity is just infinite. But this is the subject, this is the condition of absolute zero temperature. Okay, but as the temperature increases, it is seen that the resistivity of the semiconductor decreases and its conductivity increases. And even at room temperature, simply at room temperature, it conducts electricity to some extent, and then it will behave like a conductor or a metal. Okay, so whenever you talk about the resistivity or conductivity of semiconductor, you must specify the temperature. Okay, now I have mentioned here for your convenience the range of resistivity of these three types of materials. Okay, and you know the SI unit of resistivity is ohm meter. So all these values given in this table is in ohm meter. You can see the resistivity of conductors lies between 10 to the power minus 8 to 10 to the power minus 6 ohm meter. Okay, while the semiconductor has a resistivity lying between 10 to the power minus 1 to 10 to the power 7 ohm meter, and that of insulator, the range of resistivity is 10 to the power 10 to 10 to the power 14 ohm meter. And you can see that the resistivity of the semiconductor is greater than the resistivity of conductor and less than that of insulator. It is just almost in the midway of the resistivity of conductor and insulator. So in definition, I have told you that semiconductors are materials whose resistivity will lie between the resistivities of the conductors and the insulators. Okay, I have also provided here a table in which you can see the electrical resistivity of various materials almost at room temperature, or you can say at 20 degrees C, and all these values are also given in ohm meter. I am not saying that you have to remember these values. There is no need to memorize this. This table has been shown only for explaining the fact that the resistivity of the semiconducting material lies between the resistivity of metals and insulators. So there is no need to memorize all these values. It is not a good thing that you have to memorize it. Okay, you can memorize only important value. For example, if you remember the resistivity of germanium and silicon, that will be a good approach. But there is no need to remember all these things. You can see that the resistivity of metals like silver, that is Ag, is 1.6 into 10 to the power minus 8 ohm meter. All values are in ohm meter. And similarly, the copper has a resistivity almost equal to Ag, and that is 1.7 into 10 to the power minus 8 ohm meter. And you can see the values for resistivities for aluminum, Al, and Fe, ferrous, that is iron. And constantan has a resistivity of 4.9 into 10 to the power minus 7 ohm meter. But if you are talking about semiconductors like germanium, you can see its resistivity is almost 4.7 into 10 to the power minus 1, that is 0.47, you can say, ohm meter. And that of silicon, if it is in pure state, then it is 3 into 10 to the power 3 ohm meter. Okay. We will see that actually semiconductors may be oxides and sulfides and in compound form. So Fe3O4 is also a semiconductor, and its resistivity is almost 1.0 into 10 to the power minus 1 ohm meter. And like that, INSB has this much value of resistivity, and SN, that is tin, that is gray SN, has this much resistivity. Okay. And if you talk about insulator, you can see the value of resistivity for glass and mica, which is of the order of 10 to the power 10 to 11 and 10 to the power 14. So now it is clear from these two tables that the semiconductors will have resistivity lying between metals and insulators. It will be greater than metals and less than insulator. Okay. I think now this definition of semiconductor is very clear to you. Okay. Now let us see. Actually, before this lecture, we have discussed in very detail the band theory of solids, where you have also seen a particular specific lecture on the difference between metals, semiconductors, and insulators, and on the basis of band theory. And you have seen actually band gap in a solid differentiates the materials on the basis of electrical conductivity, because electrical conductivity of material depend on the band gap. Okay. And you have seen also what is the range of band gap in case of semiconductor, in case of metal and insulator. In fact, in case of metal, band gap is almost zero. Okay. In some metals, there may be some band gap, but in most of the metals, this band gap is zero. Band gap means this is the energy gap between the conduction band and the valence band, which we have already learned. Actually, when you talk about the band gap of semiconductor, it is found that it varies between 0.2 electron volt to 2.5 electron volt. Okay. Actually, this value 0.2 electron volt to 2.5 electron volt, this is much smaller than the band gap of insulators, because in case of insulators, if you talk about a particular insulator like diamond, it has a band gap of almost 6 electron volt, or sometimes you will also see there different form of diamond, the band gap may be of 7 electron volt. So the band gap of semiconductor is smaller than the band gap of insulator, and this smaller band gap actually gives the specific property to this material. Okay. Because this band gap is small but not zero, so this material at absolute zero temperature will have a vacant conduction band. There will be no electron in the conduction band at absolute zero temperature in semiconductor, and so they behave like insulator. But as the temperature is raised, some of the electrons from the valence band jumps to the conduction band, creating a hole into the valence band, and that electrons take part into electric conduction, and the material then start to behave like a conductor. And this is all due to this smaller value of band gap, because this much energy can be imparted to the material from outside by irradiating, by the fall of radiation, by heating, and so many ways. Okay. And I have shown here for a comparison the band gap of some of the elements of this fourth group of periodic table at 0 Kelvin temperature. And here also this band gap has been measured in the unit electron volt. So all these numerical values are in electron volt. And all the elements I have taken here which belong from the group 4 of the periodic table. You can see uh, carbon, that is diamond, has a band gap of 5.51 electron volt. Okay, and so it is an insulator. Okay, because this band gap is greater than 2.5 electron volts, so diamond is an insulator. Okay, but if you will talk about this germanium and silicon, you can see the values of their band gaps are respectively 0.75 electron volt and 1.16 electron volt. And this lies in this range, that is between 0.2 electron volt to 2.5 electron volt. So these two materials are the most important semiconductor. Jeremy, whenever you talk about semiconductor, definitely these two examples, germanium and silicon, comes into your mind. Okay, but Sn gray is also an element of fourth group, but it has a band gap of 0.08 electron volt, which is much smaller than this range. And so this Sn, can you say this will behave like a semiconductor? Definitely not. Sn will behave like a metal, that is like a conductor. And this Pd, this has almost zero band gap. Okay, zero band gap. And so this will definitely a metal. So in fourth group, you can see these two elements Ge and Si has a smaller band gap, but not very small, not zero. Okay, and so these are semiconductors, while carbon has larger band gap and that behaves like an insulator. And when you talk about Sn and Pd, you can see the band gap is negligibly small, and so they behave like metals or conductors. Okay, now actually as I have told you earlier, that at 20 degrees C it is observed that the semiconductor have resistivity lying between metals and insulator. Okay, this table which I have shown here, this is already at 20 degrees C, that is almost at room temperature. Okay, but as I have told you earlier, that the resistivity of a semiconductor depends on temperature strongly. When you will raise the temperature of a semiconductor, its resistivity will increase. Its resistivity will decrease, not increase. Uh, in fact, by increasing temperature, resistivity of metals increase. Okay, but the resistivity of semiconductor decreases. Okay, you can see the relation between the resistivity of a semiconductor or a metal. This relation actually holds for both semiconductor and metal at two temperatures. This rho 0 refers the resistivity of the material at 0 degrees Celsius, and this rho theta represents its resistivity at theta degrees C. Okay, and what is this alpha? You know, alpha is temperature coefficient of resistance. You have definitely learned about this formula in your lower classes. In fact, in your course in physics of 12th level. Actually, this formula which I have written, that rho theta is equal to rho 0 times 1 plus alpha theta, this holds when theta is small. But if theta is not small, then inside this bracket other terms will be also content. Higher powers of theta will be also present. That is 1 plus alpha theta plus beta theta square and so on. But if you are talking about a smaller temperature, okay, like 20 degrees C, 30 degrees C, that is not a very large temperature. In that condition, the resistivity varies with temperature almost in accordance with this relation. Okay. Actually, all game is lying in the behavior of this alpha, which is called temperature coefficient of resistance. In fact, this alpha has a negative value for semiconductors, okay, but it is positive for metals. So the behavior of variation of resistivity of metal and semiconductor in accordance with temperature is just opposite. Okay, you can see if alpha is negative, then when you will increase the value of theta, this alpha theta term will increase, but since alpha is negative, so you will have to subtract more from this one, and so the result will be less. And that's why this negative value of alpha on increasing the value of temperature theta, resistivity rho theta will decrease. And you can see this equation, rho theta is equal to rho 0 plus alpha rho 0 times theta. This is just equation of a straight line, y equal to c plus mx. Here the slope m is equal to alpha times rho 0, okay, and theta is at the place of x. Since this alpha is negative, so slope will be negative, and so if you will plot this rho theta in against of theta, you will get a straight line as shown in this figure with negative slope, okay. So it is clear from this graphical plot of rho theta in against of theta for semiconductor that on increasing the temperature theta, the resistivity of the semiconductor decreases almost linearly. But this linear variation will be valid until you are talking about the smaller temperature. At higher temperature, this linear variation is not valid. Then resistivity will decrease with theta non-linearly. And we will also talk about these things when we will discuss the theory of semiconductor in our forthcoming lectures. Okay. But as this alpha is positive for metals, okay, alpha is positive for metals. So in that condition, the slope of the straight line will be positive, and that's why in case of metals, on increasing the temperature theta, the resistivity increases. So this second figure actually represents the graphical plot of resistivity rho theta in against of temperature theta. And you can see in this condition, for a smaller value of theta, rho theta increases linearly with increase in theta. Okay. So resistivity, as I have told you, of the semiconductor is strongly temperature dependent, and that's why on increasing temperature you can see the resistivity decreases, so that at higher temperature these materials start conducting electricity and its behavior becomes like a conductor. Okay, but the same material at very low temperature, almost at 0 Kelvin temperature, it does not conduct, and so that it behaves like an insulator. So in the beginning of my lecture, I have told you that this material behaves like a conductor sometimes in some physical condition, and it behaves like an insulator in another physical condition. And what is that physical condition? One of those physical conditions are temperature. At very low temperature, but theoretically at 0 Kelvin temperature, the behavior of semiconductor is just like an insulator. But at higher temperature, it behaves like a conductor or metal. Okay. I think you have clearly understand what I am telling to you. Okay. But only increasing the temperature, we cannot increase the, sorry, there are so many factors for increasing the conductivity of semiconductor. Increment of temperature is one of the way, one of the means, one of the one of the factor responsible for increment of its conductivity and decrement of its resistivity. But there are several means for this. One of the important means for increasing the conductivity and decreasing the resistivity of semiconductor is to introduce some impurities in the pure crystal of the semiconductor. If you will just like you take the pure form of silicon and you um, mix with this silicon uh, an impurity like phosphorus, or you mix in this like Al, then you will see later on that two types of semiconductor will be resulted when this pentavalent impurity P is added to this silicon. We will get N type of semiconductor, and when this trivalent impurity will be added, we will get P type of semiconductor. All these things we will discuss in our forthcoming lecture. Actually, what happens when these impurities are added to the pure crystal, then the band gap is affected, band gap decreases, okay, and so that conductivity increases. So you can control or affect the conductivity of a semiconductor by adding some appropriate impurity to the pure semiconductor crystal. Actually, this impurity is not added in any manner, but it is introduced in a controlled manner, and this process is called doping. In fact, it is seen that if there are almost 10 to the power 6 atoms of pure semiconductor, okay, then on this 10 to the power 6 pure semiconductors atom, you should have to dope only one atom of the impurity. Impurity atom uh, and pure semiconductor atom and the impurity atom must be in the ratio of 10 to the power 6 is to 1. Okay. So this process is called doping, and after this we will get an impure semiconductor or extrinsic semiconductor, or you can say a doped semiconductor. So I have mentioned it here. You can see the conductivity and band gap of semiconductors get modified by the introduction of impurities, which strongly affect their electronic and optical properties. The process of introduction of impurities in precisely controlled manner is called doping. Okay, and the doped semiconductors are called impure or extrinsic semiconductor. It is also called doped semiconductor. Okay, so you can control the conductivity, or you can uh, increase the conductivity of a semiconductor by increasing its temperature and also by adding some appropriate impurity into the semiconductor. Okay, so there are two types of semiconductors. The first one is called intrinsic semiconductor, where the crystal of semiconductor is pure, there is no impurity, and its conductivity is controlled by temperature. Okay, but there may be a semiconductor in which we dope some impurity, and then there will be no need of controlling the temperature. By the addition of impurity, we can control the conductivity and resistivity of the material, and those semiconductors are called impure or extrinsic semiconductor or doped semiconductor. Okay, but don't think that these semiconductors are always in elemental form. Germanium and silicon, these are two most important examples of pure semiconductor, and these two are in elemental form. But there are also materials which are not elements but compounds which behave like semiconductor, and those materials have also so many practical importances. For examples, the compound semiconductors, you can see this gallium arsenide, GaAs, indium phosphide, okay, and cadmium sulfide. These are actually the compound semiconductors. Okay, In fact, you can see these compound semiconductors are formed from the combinations of the elements from group 3 and 4, 3 and 4, and group second and 6. You can see. Okay. So apart from germanium and silicon, there are other element. Okay, these are compound, but sometimes people think there are only two elements, Ge and Si, germanium and silicon, in our periodic table, which are semiconductors. But this is not correct. In fact, in our periodic table, there are 11 elements which behave like a semiconductor. Okay, and I have shown all those elements in this table. Actually, in this table, you can see I have shown the elements, some of the elements of uh, group 3rd A, 4th A, 5th A, 6th A, and 7th A. Okay, and you can see the elements which I have enclosed by these lines, that is this B, that is boron, this C, carbon, silicon, germanium, Sn, As, Sb, Se, Te, I, and Bi. All these 11 elements which have been enclosed by the line are semiconductors. Okay, so don't think that only Ge and Si are the two semiconducting materials in our periodic table, but there are how many elements? You can count it. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so 11 elements in your periodic table has semiconducting behavior. Okay, now as I have told you that semiconductors are basically of two types, and those two types are pure or intrinsic semiconductors and impure or doped or extrinsic semiconductor. Okay, actually in our second lecture after this introduction, we will learn about, first of all, the properties of this pure semiconductor and impure semiconductor. And after knowing all the properties of these two types of semiconductors and the bond formation in these two types of semiconductors, then we will learn about the carrier concentration among these, the concept of Fermi level, concept of conductivity. All these things we will learn in our forthcoming lecture, and those will be very interesting. I have a deep faith that you will definitely enjoy my lectures on these semiconductors. Okay, thank you very much.